Hi everyone. Okay, let's go through the solution for nitrogen compounds MCQ. Okay, let's look at the first question. Benzyl amine has a formula C6H5CH2NH2 and is a common precursor in organic synthesis. Which of the following statements about benzyl amine is correct? Alright, so benzyl amine here actually it's actually a nucleophile. Alright, it's actually a nucleophile because there's a lone pair on the end. So it reacts with halogenate alkane to form this compound. So the keyword here is excess. So if there's excess halogenate alkane, you should know that it undergo multi-substitution, right? So in fact, let me just run through the thought process of how this is done. Alright, so you start with this one here, CH2NH2. Alright, so this is your nucleophile. So if it reacts with a halogenate alkane, which is CH3, CH2Cl. So again, the mechanism, brief mechanism, delta plus, delta minus, it will take this carbon. Alright, it will have to kick out the Cl and kick out one H. Right, so the first part that you can draw is this one here, CH2. Alright, this N. So there will still be a H over here. Alright, so this will become CH2, CH3, right? So this process can still continue, right, with excess CH3, CH2Cl. Right, so the process will still continue. Right, so the next product you can get is this one here, CH2N, CH2, CH3, and then basically the lone pair will take this carbon, then kick out the Cl and kick out the H. Right, so if it goes again, so CH2, CH3. And of course, the last step, all right, with excess of CH3, CH2, Cl, I'm just going to draw up for you. Finally, this is what you get. All right, CH2, CH3, CH2, CH3, CH2, CH3, and there's a plus, all right, and the Cl minus, right, Cl minus, right. This will become a quaternary ammonium salt. So if you look at the molecular formula, so let's see, you have 6 carbon in the benzene ring, 6, 7, 8, 9, 10, 11, 12, 13. You have actually 13 carbon. Can you see that? So hydrogen, the benzene ring, you have 5 hydrogen. So 5, 6, 7, all right, 6, 7, 7 plus 15, which is 22. Correct. And Cl, there's one N and there's one Cl, right? So this is actually correct. Actually, one is definitely correct. Okay, it reacts with carboxylic acid to form an amide. No, carboxylic acid plus amine, it becomes a salt, right? So if I have to write the equation, it's like that, CH3, COOH. So it's just an acid-base reaction, right? It will just be an acid-base reaction. C6H5CH2NH2. So I said you're going to form a salt. So the salt will be this. So CH3CO minus, right? So you get C6H5CH2, all right, NH3 plus, right? So acid base reaction, proton donor, proton acceptor. Okay, so this is definitely wrong. It can be distinguished from this amine by the use of aqueous bromine. So the thing is this, if you look at this this amine here, it's still aliphatic amine, so it will not react with aqueous bromine. Okay, so these two will not react with aqueous bromine, right? No reaction with aqueous bromine. The one that reacts with aqueous bromine is the aromatic amine. Only this one, all right, only this one will react with aqueous bromine. So if you add aqueous bromine, you get Br, and the Br. Okay, but in this question, these two, you can't distinguish them with just aqueous bromine, right? So this is also wrong. So the answer is C. All right, the answer is C, one only. Okay, let's move on to the next question. The structures of some nitrogen containing compounds are shown below. So what's the order of increasing basicity, right, of the nitrogen containing compound? So actually this is a conjugate acid, right? It's a conjugate acid of this compound here, so of this amine here, right? It's a conjugate acid of this amine, right? Let me just draw it out nicely. Okay, it's a conjugate acid of this amine. All right, so this is actually an acid. All right, this is acid actually. Okay, this is amide. Compound K is amide, so amide we know is actually neutral, right? We know it's actually neutral. These are bases, so this one, the lone pair will delocalize, so it's less basic. Alright, compared to this one, actually the lone pair also delocalized, but just this one has a electron donating group. Alright, which means the lone pair on this end is actually more available compared to compound H. So the one that's most basic would be J. Alright, most basic, just right here, most basic would be J. And the one least basic, right, least basic must be the one that's acid, yeah? The one that's acidic, which is I. Alright, so after that, K is which is neutral. Okay, the basic, then the next one is H and then J. Alright, because J is still more basic than H, right? Because of the electron donating alkyl group. So which means the answer must be B. Alright, so the answer is B over here. Right, okay, let's move on. Okay, let's look at question 3. Okay, which statement about lactimiddomycin are correct? Okay, so let's look at the question 3. Okay, 1 mole of lactidomycin reacts completely with 4 moles of 2,4-DMPH. So 2,4-DMPH is only for carbonyl. In fact, there's only one carbonyl group here. Alright, this actually is an ester, so it's not considered. And over here, this one is like you can treat it as an amide and an amide, right? So there's only one carbonyl group, so it doesn't react 4 moles of 2,4-DMPH, right? The only carbonyl group is this one here, which is a ketone. Okay, so this is wrong. Okay, this is definitely wrong. On reacting with lactimiddomycin with hot chemical, there's no gas evolved. So is there a gas evolved from here? Right, let's see whether is there a gas evolved. Right, this question is a little tricky, so let's see whether there'll be a gas. Okay, actually the answer is there will be a gas evolved, but where will it be? It's actually over here. So with acid, alright, hot acid, it will hydrolyze the ester, and actually the alkene will also be oxidized. Can you see that? So I'm going to just draw this part here. So it's going to be OH, C double bond O. Can you see that? And when this ester gets oxidized, it also becomes COOH, right? So if you think about it, this one is the ethane diuric acid. So in the presence of KMNO4, it will be further oxidized. It will be further oxidized to carbon dioxide and water. All right, it'll be further oxidized to carbon dioxide, water. So this is the gas that is being formed. So this is out. Okay, which means it leaves us with no choice but to say 3 is the only answer. Alright, so it must be D. Okay, anyway, just run through. On heating lactimiddomycin with potassium hydroxide, there is ammonia gas evolved. So where's the ammonia gas? Yes, the ammonia gas is here. So this part here will undergo base hydrolysis. Those two amide linkages will break, and here you end up getting your ammonia. Alright, so that's correct. Okay, let's look at question number 4. Purine is a heterocyclic aromatic compound. Alright, the nitrogen atoms labeled Na and B have different basicity. Na is basic, where Mb is non-basic. Right, it's non-basic. Okay, so to take note, alright, in fact, I went through this a bit in the video that I created in the past. So this N has a double bond. So actually I'm going to just say this, all the nitrogen, this nitrogen, this nitrogen, and this nitrogen, they have a double bond. They are all sp2 hybridized. Alright, they're all sp2 hybridized. All the hydrogen are all sp2 hybridized. Is okay? All sp2 hybridized. Okay, this NB is actually, they say, is non-basic. Why? Because the lone pair would actually delocalize into the pi electron cloud, alright, of the CN and CC double bond. So actually it's not available. So for the NB, the electrons to delocalize, alright, in fact NB is sp2 hybridized. Alright, it's actually also sp2 hybridized. Okay, and the electrons in the p orbital can delocalize. So is that right? Okay, so what happens here? So based on the above information, which bond is not present? So all the carbon here are also sp2 hybridized. All the carbon here, carbon here, carbon here, all sp2 hybridized. Okay, so if you look at it carefully, in fact, in the ring, all the atoms in the ring are all sp2. In fact, there isn't any atom in the ring that's sp3, which means which one is not present is actually A already. That's the answer. All right. So maybe just to run through quickly, where is the sigma bond formed for 2sp2 and 1s? Just to give you a rough idea. So let me just erase this. Okay, so where is this bond? For this is the bond that they're talking about, is over here. All right. This carbon is sp2. All right, and this H is actually S, but since it's only in it only has one shell, it's one S, and the sp2 is in the second shell, so that's why this sigma bond is the one I've just shown you. Okay, so this is the one I'm looking at. Okay, the overlap here is a S1s and 2sp2. 2p, this is a pi bond. Yep, so all the pi bond, as you can see, all the pi bond are actually 2p and 2p overlap. Okay, so sigma bond formed from 2sp2, 2sp2. Yes, this carbon and this nitrogen is really sp2, sp2 overlap. Okay, but it's a sigma bond, of course, right? Sigma bond. Okay, so just to give you a rough idea, right? Okay, let's move on to the next question. Okay, amide. Okay, this amide, M has an empirical formula. When M is hydrolyzed by heating reflux with dilute acid, a carboxylic acid with this empirical formula is obtained. So what could be the skeletal formula of M? So if I break this part here, right, it's hydrolyzed with hydrochloric acid, you end up getting CH3 COOH. Okay, CH3COH. So let's see what is the formula. It's actually C2H4O2. Can you see that? Which means this is wrong already. All right. So if I hydrolyze this, all right, so what I'm getting is CH3, CH2, CH2, COOH. Right, COH. Right. So if I hydrolyze this one over here, all right, I'll get CH3, CH, CH3, COOH. All right, and you realize that these two, all right, these two, 1, 2, 3, 4, the molecular formula is C4H, 3, 4, 5, 6, 7, 8, H8O2, right? And the empirical formula will of course be C2H4O, all right? So which means the answer is 2 and 3. Is okay? So I hope you got B for this one. Okay, let's look at the next question. Lysine. Okay, so this was something also if you have watched my video, all right, you have gotten this. Right, so very quickly, you notice this nitrogen, all right, this is COH, right? So there's a lone pair on this nitrogen and there's a lone pair on this nitrogen. So COH is actually, the O is very electronegative, it's going to pull away the lone pair from this nitrogen, okay, very strongly because it's very close to this nitrogen. So this one actually is less available. So I'm just comparing these two bases. So this one must be a weaker base. And this one here, this end here, will be the stronger base. Okay. So if you remember the formula of Ka times Kb equals Kw. Alright. So if you have a weak base, a weaker base, you will end up having a stronger acid. The conjugate will be a stronger acid. Okay, why? Because if you have a low Kb, you definitely have a high Ka. All right, so I'm going to just draw this out very quickly. So I'm just going to look at the Ka values of these three acids. So this is the strongest acid. The pKa is 2.2, and since this part is the weaker base, alright, I will say this becomes the stronger acid, so you have a pKa of 8.9. Alright, and this one will have a pKa, in fact, sorry, it's NH3 plus, it's a conjugate acid, has a pKa of 10.5. Alright, 10.5 over here. Alright, okay, so they say which structure is the predominant when lysine is an aqueous solution of pH 9.5? So if so I'm just going to do one by one. So if the pH is 9.5, which is greater than this pKa, right, greater than this pK, means the medium is actually quite basic, right? Quite basic. So this will exist as COO minus, right? It's going to exist as COO minus. So I'm going to eliminate A already. Okay, so the next part here, so this one is 8.9 and the pH is 9.5. It's actually bigger than 8.9, so which means the medium is more alkaline. More alkaline means this guy will actually be able to donate the H+, because in a very alkaline medium, right, it will be able to, the OH minus will be able to pull out the H+. So this will be NH2. Can you see that? Alright, it's NH2. So I also now eliminate C. Right, so sorry, anyway, this should be just a CH. Okay, this should just be a CH, right? Okay, last part here, this one here, so this 10.5, so 9.5 actually is below 10.5, so the medium is actually treated as more acidic, so which means I think it will still remain as an acid at the end, right? So this one should be NH3 plus, right? So which means the answer has to be D, right? Answer has to be D. Okay. Okay, let's move on to the next question. All right, question 7. Okay, look at this structure. Which of the following will be formed when this polypeptide chain is heated under reflux with 6 moles of sodium hydroxide? So this is actually base hydrolysis they're talking about. So which of the following will be formed? Okay, let's look at the answer, the options. So how do you get this first one here? I'm just wondering, how do you get this first one here? In fact, you are actually hydrolyzing this part here, right? So this is what you get. I believe that is the product. Okay, that's the product. Okay, let's look at the next one. Okay, do you get this second product when you hydrolyze this? All right. So one of the flaw of this one here is actually this part here, because since the medium is basic, over here it should be NH2. Okay, not NH3 plus, right? It should be NH2. So that's a flaw for this part. So 2 is out, but 1 is correct. Okay, 1 is correct. Okay, let's look at 3. In order to get 3, this is where it hydrolyzes. All right, it's a basic medium, so COO minus, so NH2 and phenol. Okay, phenol is acidic, so it will react with the base to form O minus. So this is also correct. Okay, phenol is acidic, it will react with the base to form O minus. Okay, how about the last one? Okay, the last one, in order to get this, I can see that you are actually hydrolyzing this part here. So it's actually this component here. Okay, but why this one is actually wrong? Because in a basic medium, it will also hydrolyze one more amide, which is this one over here. Okay, this is an amide. So this amide linkage must be broken. So this one is not correct. Okay, so this leaves us to the answer of only 1 and 3. Okay, so this leaves us answer only 1 and 3. Can? So it's going to be 1 and 3. Okay, let's look at question 8. Okay, look at this question. When 5-hydroxyantranilic acid, okay, 5-HAA, yeah, is a tryptophan metabolite that is suspected of generating oxidative stress and neuronal death. All right, anyway, okay, it reacts with ethanol chloride followed by lithium aluminum hydride. The product was found to have a purple coloration, so with neutral FeCl3. Okay, so which means the final product must have phenol. Okay, the final product must have phenol. So I'm not going to touch the phenol. So when it reacted with ethanol chloride followed by lithium aluminum hydride, so ethanol chloride will react with the amine and not the phenol. All right, so which means the first thing you're going to get with ethanol chloride, so let me just go right down, CH3COCl. So the phenol you cannot touch, since they tell you at the end you still have phenol. All right, carboxylic acid will still remain, of course. All right, nothing happens to that. So acyl chloride will react with amine to form, to form this amide here. All right, to form this amide here. This way. Okay, so this is what you get. All right, this amide. So C double bond O CH3. Right, so this is what you get. Okay, so what happens? The next step is going to be reduced with lithium aluminum hydride. Okay, so lithium aluminum hydride can actually reduce amide to amine and carboxylic acid to alcohol. All right, so eventually the carboxylic acid will be reduced, all right, to an alcohol. Can you see that? And this amide will become an amine, so it will look like that. Okay, so if you remember, this C double bond O will become CH2. All right, and so CH3, sorry. Okay, so this is what you can take note of. So this is what it should look like. Okay, so where's the answer? So it looks like it's gonna be D. All right, so this is the answer key, D. It's okay. Okay, let's look at the next question, question 9. Okay, what are products when ammonium N-phenyl oxamate is heated with sodium hydroxide? So this is actually going to be base hydrolysis of the amide over here. All right, this is the amide. You can see I'm going to hydrolyze this. So this base hydrolysis, right? So the answer would be definitely, right? In fact, you can see already. So if I do a base hydrolysis, this one becomes NH2. All right, so the other side will be O. You can't be OH as O minus, because the medium is basic. So double bond O. All right, double bond O, O minus. Okay, so this is it. Right, so there's ammonia, but it's supposed to have ammonium, but because the solution is basic, so ammonium will lose a H plus and you end up getting ammonia. All right, so I believe the answer here should be C. Okay, let's run through question 10. All right, so the table shows 3 common amino acid. So amino acid is like that: NH2, right? CH, COH. All right, COH. And then there's an R group here. Okay, so the R group is all represented over here. Okay, there's an R group over here. So the thing about there are the tripeptides, so they're all linked to one another. All right, so it's probably looking something like this. Okay, maybe just a quick one. It will link this way. Okay, so the R group is one R group here. This is R1. I'm going to call this R1. I'm going to call this R2. I'm going to call this R3. I hope you can tell there are 3 amino acids over here that I've just drawn. 1, 2, 3. Okay, so there are 3 that's why it's called tripeptide. They're all linked to one another. Okay, so this one here, I guess you can see in general, this one here, you can see this is the R group. Okay, so this is actually your glue. Right, this is the second R group, which is your lysine, and the last one here, this is the R group, as you can see, is your serine. Okay, but what's the flaw with the first option? Because this is actually an acidic medium. So acidic medium, you realize that actually amides are neutral, they won't react. So this is the problem. Okay, they drew a amide that was protonated, so this is wrong. All right. Okay, let's look at B. Okay, let's look at B. So if you look at B, I'm just wondering why does it look over here like this? It's supposed to be C double bond O, right? So this is definitely wrong already. Okay, let's look at C. C is correct. It says the acidic medium NH3+, acidic medium NH3+. Amide doesn't get protonated, which is correct. Okay, carboxylic acid remains, alcohol also remains. So I think the answer should be C. All right, so let's look at what's wrong with this last one for why D is marked wrong. Because the medium again is acidic, so this part is wrong. It won't be CO minus. And also, I'm not sure why the alcohol lost the H plus, right? So this is also totally wrong. Okay, so that's how we do question 10. Okay, let's look at question 11. The synthesis of aromatic amide is shown below, which is the most suitable reagent. So not difficult. This is an amine. All right, amine to become an amide. All right, so you always add an acyl chloride. Okay, amine to amide, add acyl chloride. So I guess this one is pretty straightforward. You should get an answer A. All right, so this is acyl chloride. Yeah. Okay, let's move on. Okay, if some of you need help, it's this one, just like that. Okay, so I guess you take away the Cl and the H, right? So generally that's how it works. Okay, but of course there's a nucleophilic sub mechanism there. Okay, let's look at the next one. One more cryptophycin, all right, reacts completely with sodium hydroxide, which will give the number of moles of sodium hydroxide required and the number of moles of alpha amino acid. So I guess sodium hydroxide can react, can act as a base as well as a base to hydrolyze the ester and the amides if there are any. So let me just break all the esters and amides so to see how many moles of sodium hydroxide is needed. 1 mole because it hydrolyzes ester, hydrolyzes ester, hydrolyze this ester, hydrolyzes amide, hydrolyzes amide. Okay, and actually it's kind of tricky. So 1 2 3 4 5 size sodium hydroxide is already needed, but actually this one can undergo nucleophilic substitution. The Cl can be kicked out, replaced with OH, so actually you need 6. So it's either B or D. All right, 6. Right, so let's show how many alpha amino acid products will be formed. So this is a bit tricky. So you must look out for alpha amino acid. It's called alpha amino acid, right? Alpha amino acid. Okay, alpha amino acid looks like this. So NH2, CH, R, C double bond O, OH. Okay? So alpha amino acid, so alpha amino acid, right? It must only have a carbon. This is called alpha carbon. There's only one carbon between the COH and the NH2. So and of course you have the R group. So I hope I'm going to just show you where they are. So hydrolyze. Okay, and let me see here. Hydrolyze. Okay, I'm going to hydrolyze all of them, but I guess it is hopefully you can see where the amino acid. I'm going to circle because it's not so easy to show you, but this is the first amino acid. All right, so there's a carbon in between the NH and the C double bond O, so this is 1. Okay, some of you might be thinking, how about this one here? Okay, let me show you the other one first. This is the other amino acid. The alpha amino acid is over here. Okay, so 2 already. Okay, some of you might have this. So this question is a bit tricky because they drew this one here. Okay, how about this one here? So how about this amino acid? Actually, this is C double bond O. Okay, if you say you hydrolyze it, right? So I'm just going to draw like that first. Okay, notice this is CH3 over here and a H, and this is a CHH, and last part is NH2. So if you notice, I would say this carbon here is the alpha carbon, but there's actually another carbon between them, all right, between the COH and NH2, and this is called the beta carbon. This is known as a beta amino acid. Okay, there are 2 carbon between the COH and NH2. So the one that's highlighted in red is actually a beta amino acid, so it's not considered. All right, so that's why the answer is actually B. Right, the answer is actually B. There's only 2 alpha amino acid. Okay, let's run through the next part. Okay, let's look at question 13. Okay, which are the possible products formed when the following is reacted with lithium aluminum hydride? So lithium aluminum hydride, what it does, it can actually break this ester linkage, and both ends, actually, as you notice, both ends will actually become alcohol. Alright, so this part become alcohol and the other side also become alcohol. So I'm going to hydrolyze this part here. Let me just draw it out. Okay, I'm going to break this and break this. Okay, the ester linkages. So with firstly, alright, the ketone over here, this ketone here will be reduced with lithium aluminum hydride, so it becomes a alcohol. Okay, a secondary alcohol. This part right here, like it follows this, so it's like this part here. Can you see that? So it becomes also an alcohol. Alright, so I'm going to draw just OH. Okay, right. So how about the other side? The other side is OH. Okay, so this part here also becomes an alcohol. Can you see that? So the other side is a alcohol here. The third part, I'm drawing this one here. Okay, so the third one is this, but if you remember amide also can be reduced by lithium aluminum hydride to form amine. So the C double bond O will become CH2, so this is my final answer. Okay, so basically I'm going to have all these. So I guess okay, this is out. Alright, you don't have that. Oh, this one too is there because it's the same as over here. And you can see that this product here, okay, this product here is the same as 3. All right, so which means the answer is 2 and 3. Okay, this product here is the same as 3. Right? Okay, now let's go through question 14. All right, so this is another lysine question, right? Let's run through. Okay, so this lysine amino acid, I'm going to say a few things first. So this is a carboxylic acid, all right, and this is a carbon. We call this alpha carbon, right? The carbon that's next to the main functional group, which is the acid. Yeah, it's called alpha carbon. I'm just gonna say that this is the main chain, right, of the amino acid, and this is actually the side chain, right? This is the side chain. Normally we write it as R group. Okay, so there's this is the amino group, but it's on the side chain, and this amino group we say is on the main chain, right? So let's run through. Okay, so maybe I'm just going to draw everything nicely again. So this first one, I'm going to call it A1. It is completely protonated. This is in a very acidic medium, so I'm calling it A1. So I wrote it over here. This is the beginning of the graph. All right, so if you remember, this acid group has a pKa of 2.2, right? 2.2. This is the most acidic one. So the next most acidic group is this one here, the conjugate acid of the main amino group. So on the main chain, I mean. So this one we know that, which I went through already, this pKa 9.0, the next most acidic, and the R group, this R group here, right? The R group, this NH3 plus is the weakest acid. So I'm going to write down pKa 10.5. All right. Okay. So once you add a base, right? Add sodium hydroxide. The most acidic one will get neutralized first. So I'm just going to draw this. This is what happens, right? The most acidic group, which is COH, will lose the H plus and become CO minus. I'm going to call this B. In fact, it's already written down for you. So this is B. Can you see that? Okay, the next equivalence point is actually this one here, C. So very quickly, so the next acidic group that will be neutralized will be this one here. This is the next most acidic group, which means it'll be able to lose the H plus more easily than the NH3 on the side chain. Yeah. So this one becomes NH2, right? And this is I'll say C over here. All right, so let me just circle. So this is the next equivalence point. Okay, the graph didn't show the last equivalence point, but I'll just let it be. Okay, which is actually D. Like if you have to draw it out like that, this is probably D, and this is the one. Okay, the last acid will be neutralized. Yeah. Okay, let's run through the answers now. Which statements are correct with respect to the curve above? The alpha amino group has a pK value of 10.5. What I mean by the alpha amino group? Okay, what it means is this. So this is the alpha carbon. All right, so this alpha carbon. All right, so they say the alpha amino group is actually talking about this amino group. Okay, but they say has a pKa of 10.5. But anyway, firstly, the alpha amino group actually is being protonated. So once it's being protonated, it's an acid, but actually has a pKa of 9.0. Okay, 9.0. So this one say 10.5, so it's actually wrong. Okay, equal amounts of these two were present at point A. So point A, right, you have equal amount, you have an equal amount or equal concentration of A1 and B. All right, which means these two, right, equal amount A1 and B. So this is this part. So I can see that this is A1, all right, this one that they've drawn, but this one looks a bit strange, all right. So what is B? B, this part here is let me see here. Okay, this part here is supposed to be NH3 plus, all right, and this one is supposed to be CO minus. Can you see that? Okay, but it's not. So this one is also out, right? So you have A1, but it didn't draw B for you. Okay, the major species present at point C has no net charge. So let's look at point C. Point C is your Zwitter ion. That's right. Okay, this is your Zwitter ion. So it seems that this one doesn't have any net charge. So the answer is definitely correct for point C. The major species present at point B will migrate towards the cathode of a electrolytic cell. So cation ions will migrate to the cathode. So if you look at point B, let's look at point B. Okay, point B, what's the net charge? there's a plus here, there's a plus here, and there's a minus. Can you see that? So the net charge is still a plus, right? So we can take it to be a cation. So cation will migrate towards the cathode, right, which is the negative electrode. So this is definitely correct. So the answer is C. Okay, so the answer is C for this question, right? Okay, so lysine questions are kind of popular, right? Let's look at the next question, right? Let's look at this. Okay, compound A. Okay, upon which of the following statement is true? Upon reaction with hot acidite chemotherapy, an organic compound containing 5 oxygen atoms is formed. So let's see, is that possible? So what happens is this, you're gonna hydrolyze because of the acid and the heat. So it's gonna hydrolyze the ester linkage, right? So I'm gonna just draw what you're gonna get, all right? So you're supposed to get this one first, all right? Just draw it out first. Okay, this is after hydrolysis, all right? After hydrolysis. In fact, this one is a amide linkage, so it also hydrolyzes, all right? It hydrolyzes, so this is what you get. Okay, but the fact that there is a KMNO4, there's oxidation. So this is a secondary alcohol. This is a secondary alcohol, and this is a tertiary alcohol. Can you see that? So in the end, your product will be this. So secondary alcohol gets oxidized to a ketone. The tertiary alcohol doesn't, nothing happens to it. This becomes a ketone, all right, COOH. So let's see whether it makes sense. Containing 5 oxygen atoms. So 1, 2, 3, 4, 5. That's right. Okay, 5 oxygen atoms. So the first statement is correct. Okay, the first statement is correct. Okay, let's look at the next one. Compound A has a total of 6 stereoisomers. So let's look at compound A and whether it has 6 stereoisomers. So how many chiral centers are there? Right, I'm just going to circle 1 chiral center, okay, 2 chiral center, 3 chiral center. So it's actually 2 to the power of 3, which means it's actually 8. So this is definitely wrong. Again, you have 3 chiral centers here. Okay, it's lithium aluminum hydride will actually reduce the ester. All right, actually will reduce the ester. So let me take away this first. Okay, it will actually reduce the ester and also reduce the amide. So let me just draw out the products. So the ester here will break. Okay, but the amide, it will not break. So the ester over here, in fact, it will become, all right, actually it will become actually it become an aldehyde first. Okay, but the aldehyde will be reduced to a primary alcohol. All right, so this is one of the product. Okay, one of the product. On the other side, you have an alcohol. Okay, on the other side, you have an alcohol. Let's go and draw this first. This one's okay. So the alcohol here still remains, right? For the amide will become amine. So the C double bond O will become CH2. So this compound actually has 1, 2, 3. It has actually 3 OH groups, all right, and 1 OH group, right? But here they say 4. So I guess this is also wrong. So the answer is C. Are you me? Right, so you just have to learn that when an ester gets reduced with lithium aluminum hydride, it forms 2 alcohols, or alcohol on both sides. Are you me? So this is how it works. Okay, let's move on to the next part. Okay, question 16. How many amide linkages exist in compound W? Right, so let me just highlight all the amide linkages. So 1, okay, 2, 3, 4, 5. All right, so I hope you can get 5 amide linkages. Right, so the answer is A. Okay, this is actually okay. Okay, let's look at next question. Electrophoresis is a technique of separating and identifying amino acids. Okay, so with a buffer at pH 4, which statement is true? Right, so this compound here, so tyrosine, I'm going to just draw it out first. So tyrosine, right, at pH equals to 5.7, it is actually a Zwitter ion. So I'm going to draw the Zwitter ion like this. Okay, it's probably a Zwitter ion like this. So it's NH3 plus O minus. Yeah. So glutamic acid, if the pH is 3.2, it exists as a Zwitter ion. So I'm going to just draw the Zwitter ion. Okay, sorry. Okay, usually the Zwitter ion, the acid it will come from the main carboxylic acid group. This is the R group. Okay, so for glutamic acid, this actually is a stronger acid. Yeah, the COH on the main chain is a stronger acid. So I'm just going to draw it out over here. So this is what it should look like. Okay, so this is beta ion. So what happens, which statement is true? So at pH 4, okay, I'm going to draw what it looks like at pH 4. At pH 4, okay, at pH 4 means the medium is actually more acidic. So more acidic, what will happen is this will exist as COOH, alright, at pH 4. So this one, if the pH is pH 4 means it's more alkaline compared to pH 2, right? Now more alkaline, it will probably lose a H plus, take away a H plus from here. Okay, I take away H plus from here. Okay, because it's actually more alkaline. Yeah. So if this case, you can see that this actually becomes an anion. And actually this is a cation ion. Can you see that? This is a cation ion, this is an anion. So let's look at the answer here. So if it's cation ion, it will migrate to, migrate to cathode. Alright? And if this is anion, it will migrate to anode. Okay, why I say anion? Because there's 2 minus and 1 plus. So net is still a minus. So I think it's anion, it will migrate to the anode. So if you look at it carefully, it should be D. Tyrosine moves towards the cathode and glutamic acid moves towards the anode. Alright. Okay, so let's move on. Okay, let's move on to the next question. 18. Okay, saccharin is artificial sweetener. Alright, and then it's manufactured from metabenzene through a 4-step synthesis. Okay, let's look at what is step 1 and step 2. Okay, step 1, if you notice, what is step 1, right? Okay. This sulfur is actually joined to the benzene ring. Okay, this sulfur is actually joined to the benzene ring. So in this case, usually we take it as this is actually a electrophilic substitution reaction. So the benzene ring, you kick out a H and then you put in the sulfur, right? So it's electrophilic substitution. I'm gonna pick B or D. Alright, then they ask for the next part. So if I have to draw it out, is this part, step 2. It looks like that, double bond Cl. Alright. So with ammonia, then the Cl was kicked out and replaced with NH2. So you can treat it as delta minus, delta plus, right? Ammonia, the lone pair on N, alright, acts as a nucleophile. It will attack the sulfur and kick out the Cl. Alright, so since is attacking the sulfur and removing the Cl, it's a substitution reaction, and this is a nucleophile, isn't it? Alright, so it's going to be nucleophilic substitution. Alright, so the answer will be B for this. Right? Okay, let's move on. Okay, I'm going to show you this, just show you something about step 1. If you notice step 1, right, this component, maybe I just draw it out nicely so maybe everybody can see what's happening. So it actually looks like this. OH, double bond O, double bond O, Cl. Okay? So what is the electrophile? If you look over here, this SO2, right? SO2Cl looks like this. Right? So you notice in this part, the electrophile, what's the electrophile? The OH was kicked out because O is more electronegative. It will pull the electrons closer to O. So what happens is OH minus came out and sulfur became a plus. So this plus here is really your electrophile. Okay, this is the electrophile. That's why it will be able to attack the benzene ring. Okay, so that's why we call it electrophilic substitution. Right? So it'll give you a better idea of what was happening. Okay, so this was actually electrophile. Okay, let's move on. Question 19. Okay, which of the following trends are correct? Okay, the boiling points of alcohol with the same molecular formula increases from primary to secondary to tertiary. The boiling points of alcohols with the same molecular formula increases from primary to secondary to tertiary. So actually what it really means is this. If it's a primary alcohol, say I draw for you a tertiary alcohol first. Alright. Then if I draw a secondary alcohol, Okay, and I'm going to draw a primary alcohol. Okay, let's draw a primary alcohol. Take away this. Okay, but they all have the same what? Same molecular formula. Alright, so what's the difference is over here they all have hydrogen bonds, so it's actually typically the same. So but this is a straight chain and this is actually branch. So branching will always result in a smaller surface area, right? Smaller surface area. So because a smaller surface area imply weaker ID, or I probably say it's less extensive ID. Okay, because smaller surface area, so less extensive ID, can? Okay, less extensive ID. So which we imply it has a weak lower boiling point. Okay, because weaker, less extensive ID, you end up having a lower boiling point. So they say it increases, so this is definitely wrong. Okay, so this one would have a larger surface area. Primary alcohol have a larger surface area, more extensive ID, a higher boiling point. More energy is needed to overcome that. Okay, the pH values of the aqueous solutions increases, which means it becomes more and more basic, right? So the first one is the acyl chloride. So remember acyl chloride in the aqueous solution, because they already mentioned in aqueous solution, means in water. All right, in water, you form CH3, COOH plus HCl. So this is very acidic because of the HCl. All right, then this one carboxylic acid. Okay, yeah, slightly less acidic because compared to acyl chloride, it produces HCl, so it's actually going to be most acidic. So next most acidic, this one here. All right, in fact, this is actually neutral. Okay, this neutral, and now there's an amine group, right? So this is actually basic. So which means this statement is definitely correct. Okay, this statement is correct. So this, but they're asking for which one incorrect. So this is correct, but one is incorrect. Okay, the ease of hydrolysis of the chlorine atoms decreases from chlorobenzene to chloroethane, all right, to ethanol chloride. All right, this is actually not true. The ease of hydrolysis actually increases, right? Increases. So this one, you can't break this CCl bond. So with sodium hydroxide, because this is partial double bond character, this bond easier to break, and then this is the easiest to break, right? So the ease of hydrolysis increases. So remember, this one is the easiest to break because this carbon is attached to two highly electronegative atoms, right? So this carbon can be most easily attacked by the nucleophile. In this case hydrolysis, you're talking about the water, right? So this is actually incorrect because actually it increases. All right, increases. Okay, so it's 1 and 3. Okay, now true option 4, the pK values increases from ethanoate ion to phenoxide. So let me just draw it up first. Ethanoate ion is this, all right, to phenoxide ion to ethoxide ion. Okay, so now they are talking about bases, right? Bases. So so I'm going to, okay, maybe I'm going to do this first. So I'm going to think in terms of acidity, okay? Acidity. Okay, I'm going to draw the acids first. Okay, in terms of acidity, right? In terms of acidity, all right? Acidity. This is a stronger base, strongest acid, followed by phenol, followed by alcohol. So we learned the concept of Ka times Kb, isn't it? Is the inverse. So a stronger acid will give rise to a weaker conjugate base. So if I look at basicity, all right, basicity, it'll be the opposite. So it'll be this way. So in fact, this will be this one here will be the strongest base here. You see that? So let's see whether it's true. The pKb value increases. So which means pKb value increases means it becomes a weaker base. Okay, a weaker base. Okay, the pKb value increases means this. So I say low pKb to high pKb, right? So this low pKb means high Kb, and this is low Kb. So they're actually asking you to arrange from a stronger base to a weaker base, right? Stronger base to weaker base, but actually stronger to weaker, but this is the strongest base, so actually it's incorrect. Okay, it's actually incorrect. Okay, so it's actually incorrect because this actually is the strongest base, but they want you to arrange from strongest base to weakest base. So 4 is incorrect. So which statements are incorrect? 1, 3, and 4, right? All of them. Yeah. So this question is a bit demanding, right? Okay, let's look at the next part. Let's look at question 20. Okay, let's look at question 20. The following are 3 amino acids. Which of the following represents dipeptides formed from these amino acids? So I hope you take note of this. So generally when you form amino acids, right? Okay, generally when you form amino acids, you must realize that this is the R group. R group. So when you form amino acids, you always take away the OH. Okay, you have to take away the OH and the H on the OH from the COH and the H from the N. Okay, but take note, you always remove the water from the main main chain. Okay, from the main chain, not from the R group. Okay, so you have to circle the R group to make sure you understand where are the R groups first. So for this molecule, you can see that this whole thing is your R group. All right, so for this one, in fact, it's like that, but this is your R group, of course. And for this one, this is your R group. Okay, this is your R group. Okay, so if you're gonna form an amino acid, you're gonna use the NH2 and the COH from here, the NH2 and the COH from here, and the NH2 and the COH from here. Okay, so which of the following represents the dipeptide formed from these amino acids? So let's take a look very quickly. Okay, I'm just gonna draw a line here because this is the 2 amino acids. So if you studied this properly, you'll notice that this is fine. This part came from the main chain. The COH came from the main chain because this is the R group, right? This is R group. Okay. So so the R group is over here for the other molecule, right? So this is the original was NH2 from the main chain. So this is definitely correct. Okay, let's look at 2. If I break here, okay, you will notice that this one is 100% wrong already, because over here this is for amino acids, this is my R group. Okay, and I told you you must use the COH from the main chain. Okay, you can't take from the side chain. So this CO actually came from the side chain, right? So this is I'll cross this out. This is not possible. So let's look at 3. I'm just going to draw a line here first. Okay, and again you realize that this part, right, this is actually from the R group. Right, so this one amino acid, this another amino acid, but this amino acid they use the R group here, so this is also wrong. Okay, this is wrong, this is wrong. Okay, let's look at the last one. Okay, last one, if I draw a line here, okay, you notice that which is okay because the R group is over here. This one, the R group is over here. Can you see that? Okay, so they use the NH2 and the COH, NH2 from the main chain. For this one, the R group is over here. Can you see that? Okay, R group for the other amino acid, the R group is over here. Alright, so they use the COH from the main chain, so this is correct. Okay, so the answer is 1 and 4 only. Yeah, 1 and 4 only. Okay, let's look at question 21. Okay, given that Coca-Cola has no sugar at a pH of 2.5, what is the structure of the major species of aspartame present? Alright, so it has a pK value of 3.2 and 9.5. So there are 2 acidic groups here, right? There are 2 acidic groups here. So the smaller pKa would be, of course, be the stronger acid. So let me just draw it out here. Right, so I can see that this one here, this is the acidic group, is pKa 3.2. Okay, 7.9, the other acidic group, actually you can see ester is neutral, amide is neutral, so the acid group is actually NH3 plus over here. Alright, NH3 plus, so this one is the pKa 7.9. Alright, okay, so even with a pH of 2.5, right, pH 2.5 means very acidic. right? So pH 2.5 means it's below 3.2 and below 7.9, which means both parts will be protonated. Okay, both parts will be protonated. So I won't touch these two because these two are neutral, right? Ester and amide are neutral, so don't touch it. So the answer has to be, okay, let me look at it. Yeah, so the answer has to be B, isn't it? Okay, so this is protonated and yeah, COH, acidic medium, and the other two, you don't touch them. All right, so this is wrong because I don't know why they put a H plus over there, even though amide is neutral. Okay, I don't know why they put a O minus there. That's wrong. Yeah, this is also wrong. Okay, so take note. So this is how we do question 21. Okay, let's look at the next question. All right, let's do the next question. All right, so which reaction will the oxidation number of carbon change by 4? Right, so let me just draw it out nicely. Okay, all I need to do is look at the atoms around carbon, yeah? Okay, so very quickly, oxygen more electronegative than carbon, and it's a double bond, so I'm going to say that the O here, the oxidation state is -2, carbon here put +2, sorry. Okay, this is a single bond and the N is more electronegative, so I'm going to put -1 + 1. Okay, between carbon and hydrogen, carbon is more electronegative, so it's a single bond, so -1 + 1. Can you see that? And then you sum it all up, okay, and you notice that this carbon oxidation state is +2. Right, so let's look at the next one, CH3. Right, so I only actually have to look at around the carbon. That's good enough. Change it. Okay, so let's run through. Okay, so carbon more electronegative than hydrogen, right? So -1 + 1, -1 + 1, -1 is it -1 + 1. Okay, nitrogen is more electronegative than carbon, so it's single bond, -1 + 1. If you add all of them together, all right, so it will be -2. Can you see that? -2. So from +2 it dropped to -2. The change is actually 4. Okay, there's a change by 4, right? So +2 to -2, there's a change by 4. Okay, let's try this next one. Okay, it's pretty similar to this one here, right? Can you see? It's very, very similar. So this carbon, I'm just going to skip it. This carbon is -2. Okay, -2. All right, so let's try this. H. Okay, only look at around the carbon. So -2 + 2. O is, this is single bond, right? Between C and O is a single bond. So I put -1 + 1, -1 + 1. So let's calculate. In fact, this is the net is +2. Okay, so from -2 to +2, the change is again 4. Right? Okay, let's try the next one. Okay, let me just, okay, this one is quite easy. Carbon dioxide, right? Okay, carbon dioxide. I think you can tell carbon here already is +4. You see it's +4. All right. So let's do the last part here. Okay, so -2 + 2. Okay, carbon is -1 + 1, -1 + 1. Right, so you sum up, oh, it's actually 0. So 0 to +4 is, so the change is also 4. So which means actually all of them are true, A. Okay, so all of them are true. Okay, let's do the next one. Okay, they say the active form of enalaprilat can be formed when enzymes in the body hydrolyze the esters found on the molecule. Okay, so I'm going to highlight this. The active form of enalaprilat can be formed when enzymes in body hydrolyze the ester. So the active form is because normally you have a chiral carbon, all right, and then you have enantiomers. One of them will be the active form and one of them will be the inactive form. Yeah. Okay, so which of the following is not true? Okay, which of the following is not true? Enalaprilat turns orange aqueous dichromate green when heated. So let's see, will this happen? Okay, so you're asking, will anything be oxidized? Will anything be oxidized? So if you look at it carefully, I think you can't really oxidize anything at this point, but you can hydrolyze it because there's actually acid and heat, right? So you notice what are the functional groups here. This is actually an ester. You should write down this ester. This actually is amine. This part's amide. Okay, and this of course carboxylic acid. right? So actually when there's heat and acid, it will hydrolyze the ester. Okay, it will just hydrolyze the ester. So it's actually like this, C double bond OO, CH2, CH3, correct? Okay, so the ester will undergo hydrolysis. So this is because of the acid. Okay, this is because of acid and the heat. So this one will become CH3, CH2, OH. I'm drawing this side here. Alright, so this can be easily oxidized, right, by dichromate. So it will be oxidized to a carboxylic acid. So the observation for dichromate, for this step, right, it will be orange to green. So this statement is actually true. Everybody, one not true. Okay, it does not react with 2,4-DMPH. So there's no ketone or no aldehyde. So it doesn't react. This statement is true. It doesn't react with 2,4-DMPH. It reacts with 2 moles of ethanol chloride. Okay, which part of it will it react with 2 moles of ethanol chloride? In fact, it should only react with 1 mole of ethanol chloride. Okay, why? Because there's an amine group. So amine plus ethanol chloride, acid chloride will give you an amide. Okay, the rest it doesn't react. Right, ethanol chloride only reacts alcohols or hydroxy compounds and amines. So but there's only one amine over here. So this is false. Okay, so this is not true. Answer is C. The active form has this structure. So they say the active form, right, can be formed when enzymes hydrolyze the esters, alright, found on the molecule. Alright, so what it means is once you hydrolyze the ester linkage here, this is what you get. Right? So this is actually true. Okay, this is actually true. The active form is because this carbon is actually chiral, and probably in fact there's more chiral carbon also. Okay, but this is the one they're looking at, I guess. Okay, anyway. Okay, so C. Okay, let's look at next one. Question 24. Consider the following compounds. Which of the following shows the compounds arranged in order of increasing pKb? So increasing pKb means low pKb, alright, to high pKb, right? So which means it's a high Kb to low Kb, right? So which means it is a basic, most basic, right? Most basic to least basic. Okay, so least basic. So I'm just hoping you can see that, right? Most basic to least basic. Okay, let's see which is the most basic. I just will write the functional group out. This is amine. Alright, in fact they are both secondary amine. Alright, this amide and this amine. Okay, I'm going to write this, be more specific. Phenylamine. Right. So the least basic, is amide, which is actually neutral, which is I'm going to put 3 here. Alright, and I guess phenylamine is less basic than the other two aliphatic amines because the lone pair can delocalize into the benzene ring, less available. I'm going to put 4 here. Alright, so between these two, because of the O here, right, O is electron withdrawing. O is very electronegative. It's going to pull away the lone pair from here, so this one becomes less available. So less available means it's a weaker base, so which means I'm going to put 1 here. Alright, and probably 2 is the strongest base. Alright, so that's why the answer for this will be B. Okay, next one. Okay, a peptide contains 7 amino acid residue. Alright, when it's partially hydrolyzed, the following dipeptides and tripeptides are produced. So it means, this is what it really means. Okay, it's a 7 amino acid, 1 2 3 4 5 6 7, right? So the thing is this, they are actually breaking up. So if you break here and you break here, you probably can form like a dipeptide and a tripeptide, a dipeptide. Or you can probably break other places. Maybe like you break here, so you get a tripeptide here, and maybe you break here, like here, but maybe you break here, you get dipeptide. Okay? So you can they say they give you all these, right? So maybe this is probably how I would do this question. So what could be the structure of this peptide? Okay, I'm going to look up whether this dipeptide is present in any of them. Alright, so I'm going to glycer, right? So glycer, I can see it over here. Glycer, and glycer, which means it's still possible for all of them. Okay? Alright, okay, so I do some elimination. ALA, MET. Okay, ALA, MET. Do you see ALA, MET? Yes, I see it here. I see it here. I see it here. Oh, I don't see it here, right? This one, no AL. So this is out already. Okay, so we do one by one. Okay, this is out. Right, so let me take away, easier. Alright, just do some elimination. I think it's easier we do by elimination. So glide, ALA, glide, ALA, glide. I don't see in the option B. Glide, see, I don't see option B. Glide, ALA, glide, I see option C. So B I will cancel out already. Glide, ALA, glide, I can see it over here also. Alright, so which means left A and C. Okay, let's see whether you have LYS. Okay, lysine. Okay, so let's see whether you can see SER-LYS. SER-L, I see it here, I see it here, I see it here. Okay, actually I don't have to look at A and C already, what I'm doing. Okay, I don't have to look at I don't have to look at B and D already. So I'm just gonna look at A and C, right? So okay, yeah, so I still see it over here. So which means this is the determining factor. Meet, glide, ALA. Okay. Okay, so let's see. Meet, glide, ALA, I see it here. But I don't see it in C, so I can cross out C. Alright, so that's why the answer is A. Right, so that's how we do these questions. Alright, so please review whatever you've done for the MCQ and make sure you can do it in your exam. Thank you for watching the Twig Learning Center chemistry tutorial. I hope you learned something new. Don't forget to click the subscribe button so you'll be updated when new videos are posted.